Okay, so with this one, we kind of have two parts. The first one is just a brief little, hey, talk about the forces, and then the second one is a little bit more involved. But so what we're saying here is a spring with unstretched length L1 is hung vertically with the top end fixed in place, as shown in figure 1 below. A block of mass M is attached to the bottom of the spring, as shown in figure 2, and the spring is a length where L2 is greater than L1 when the block hangs at rest. The block is then pulled downward and held in place so that the spring is stretched to a length L3 is greater than L2 as shown in the figure. So the first thing we want to do, oops, I gave away the answer, oh no. The first thing we want to do is just kind of talk about what forces are acting on it. So we can do oops, that's not what I wanted, a quick little force diagram to think about what contact forces we have acting on it, and then go from there. So we can see that we have definitely this contact force from the spring, and it looks like that spring wants to return to this equilibrium position. So it wants to pull our object upwards. So we have this spring force that is acting upwards. In this case, this block is also not moving. And then let's think about it. We also have this hand is pulling our thing downwards. It says that our hand is pulling it down. So we have a force of the hand acting on the block. And then finally, the block has mass, so we know that it has this gravitational force pulling it downwards. So that's just kind of a quick little, quick little force diagram. It won't help us so much in this case. So with this one's kind of a tricky question, and it really comes down to us defining our system and being clear about our system. So the student releases the block. Consider the time during which the block is moving upward towards its equilibrium position and the spring length is still longer than L2. So kind of in this quick little motion where we go from the lowest point to a little bit before L2. In a clear, coherent paragraph length response that may also contain diagrams and/or equations, indicate why the total mechanical energy is increasing, decreasing, or constant for each of the systems listed below. So system 1 is just the block. System 2 is the block and the spring. System 3 is the block, the spring, and the earth. And we want to talk about is E1, E2, and E2, the total mechanical energy of systems 1, 2, and 3. Are they changing, increasing, or decreasing? What's going on with them? So this is kind of a lot. But yeah, so let's first think about doing one of our LOL diagrams. So I've kind of set up these two situations and kind of written out what's happening at each one, just to think about where's this energy coming from, where's the energy in our system. So at A, we have this spring is at its very lowest point. Our block is not moving, we just released it from rest. The spring is stretched out, and we're at this 0 height. So we're at this height that we can say, oh, well, that's 0 meters. Anything above from there gives us gravitational potential energy, but this is the lowest that we're going to go. So we have this height of 0. So that's going to help us out thinking about what's happening here. At this position B that I'm marking, kind of the second location that's below L2, our block is moving. The spring is less stretched than it was before, but we definitely still have some stretch of the spring. We're not at this equilibrium. And our height is above 0 meters. All right, so let's kind of take what we just qualitatively did and turn that into an LOL diagram. And I'm going to use the LOL diagram for the whole system. I'm going to first consider everything a part of our system. So we're kind of, if we're keeping track of what's going on, we're kind of doing it for this E3. We're going to track out the total mechanical energy in our whole system, the system being the block, the spring, and the earth. So let's do it for everything. So let's do our checks. At A, we're not moving, so we don't have any kinetic energy. At A, our spring is stretched, so we do have spring potential energy. So that's good, we have that. And then we're at 0 height, so we have no gravitational potential energy. And what I'm going to do is, we kind of did this early on with our LOL diagrams. We kind of like did little boxes. I'm going to do little boxes here instead of bars, just so I can think about how many there are, how many units I'm moving around. I don't really have a number for how many boxes. Like I'm not like, oh, one box represents 1 joule of energy or something like that. I just want to still just be able to visualize how many units of energy I have and where those are all going. So instead of some sort of like rough graph with a bar, I can more specifically say, oh, I have this many units of energy to move around. I was hoping that I could, there we go. So let's say I have 6 units of energy to kind of pass around. All right, so now let's look at this position B. At position B, we have these things to choose from. At position B, our block is definitely moving. So we do have some kinetic energy. Our spring is less stretched than before. It's still, oh, sorry, this B. Our spring is less stretched than before. It's still stretched, but not as much. And now we're at some height above 0 meters. So if we think about what kind of energy we have, we went from, this would come back. So we went from not moving to moving. All right, sorry about that. So we went from not moving to moving. Oops. So we're going to have some kinetic energy. I had to close this note-taking thing because it was freaking out. So we have some kinetic energy. I don't know how much, but we have an increase. We went from a big stretch, so lots of spring potential energy, to just a little bit. The spring is definitely stretched a lot less. And then we have some change in height. We see, oh, we're above this 0 height. So we can kind of split it up like that. Again, these units, these boxes don't really mean anything, but they help us keep track of where our energy went and just kind of make sure that we're keeping it all constant. So we had 6 boxes on the left side of position A, and now we have 6 boxes on the right side of position B. So yeah, now what we want to do is kind of break it down into the systems that we're looking at. So this was for system 3. So we could write about system 3 if we wanted to, but let's just let's hold off to the end a little bit. So the first system, system 1, is for a situation where the only thing in our system is the block. So let's do that. Let's just look at it for the block. So if we have just the block, then let's think about where this energy comes from. Let's think about what's going on. So the block can't have any spring potential energy because it's just a block. It's not a spring. The spring is not included in our system here, so we no longer have this. I guess I could erase it. So we no longer have that, and we don't have any potential energy. So we start off with just the block of having no kinetic energy, and then the same thing over here. The block can't have spring potential energy, and then what's a little bit weird and a little bit hard to think about, the block can't have gravitational potential energy either. That gravitational potential energy is this interaction between the block and the Earth. So if we didn't have the Earth here and we were doing this, the spring wouldn't gain any potential energy. If we held the block right here and we weren't on Earth, it would just stay there. It wouldn't want to be pulled down to the ground because there is no ground. There's no Earth. There's no gravitational pull on this. So the block itself can't have potential energy. It needs this interaction with the Earth because the Earth is what's doing that pulling. It's what's going to give the block energy as it's falling. So we can't have that. So this is really all that we have for system 1. All right, and then let's do system 2 really quick. So 2, again, is the block. This time we have the spring, but we don't have the Earth. So really the only energy that we're getting rid of is the gravitational potential energy. And we see, okay, this is system 2. We are allowed to have the spring potential energy because the spring is part of our system. So now let's think about what happened. Let's start off. So we can say, well, for system 1, so E1, the mechanical energy in system 1, again, remember mechanical energy just stands for kinetic and potential. So really all the energies we're looking at here. For system 1, this one right here, we see, oh, well, the mechanical energy went up. The total mechanical, or let's say E1, increased because we already, and maybe I'll type it instead of writing it. But so we can say E1 increased. The block went from having no motion to having some motion before it reached L2. the block had no kinetic energy in the beginning, and as it moved, or as, I don't know, as time went on, the block sped up and had and was moving with a velocity before L2. Because it has a velocity, it has a kinetic energy. I don't know. So the kinetic energy went from 0 to some positive value, meaning the mechanical energy of the block system increased. And then maybe I'll add a little bit of something saying we don't have a change in potential energy because the only things that can supply potential energy is the spring and the Earth block system. Without the spring or the Earth, we can't have any potential energy. All right, so we kind of covered our bases there. So that's for E1. Then we can say E2, we have this decrease. So we see in E2, our total mechanical energy has decreased. E2 has decreased. The block speeds up, gaining kinetic energy. The spring goes from a stretched position to closer to equilibrium. Because the stretch of the spring is decreasing, the amount of spring potential energy is decreasing. Yeah, so that's kind of good. Yeah, maybe we should say something about where the other energy went. Whatever, we're pretty good. We have our diagrams to help us out. And then for 3, E3 has remained the same. The full interaction here is between the block, Earth, and the spring. All of the forces acting on the objects in the system are contained within the system. We have no outside forces acting on the system, which means that within our system, energy has to be conserved by the conservation of energy. So this last one just saying, oh, well, we're dealing with the whole system. We have no external forces. We know that work occurs when an external force acts on our system, but here we have no external forces acting on our system, so energy has to be conserved. All right, so I feel like that is an okay answer. There's no key for this, so I don't know what the College Board specifically wants, but I feel like we've covered all of our bases and talked about all of the energy in all of the systems. And this diagram is something that we could include if they asked this question, because it helps us think about where the energy is going and kind of tracks out what's going on in each case. But yeah, that is that one.